Good evening and welcome to the 15 Futures webinar. My name is Nađa Memić and I am the coordinator of the series. This time the topic is Black Magic, Radio Frequency Engineering, a field that is not in the spotlight but has been crucial for a number of technologies including Bluetooth and Wi-Fi. The topic is brought to us by our honorable guest Nađa Memić, a senior manager for the RG Engineering Design Group at Lockheed Martin Space Company. She started her career in space industry as a lithium-ion battery designer for a leading U.S. battery provider, EnerSys. She is currently enrolled in the System Engineering Master's Program at Denver University. Nađa, thank you so much for taking the time to be with us tonight.
All right, and now let me know when you want me to start.
Right now?
All right. Now would be good.
Yeah.
All right. So I was telling Anna, this is a little bit unusual for me because I'm used to more interactive, and I feel like it's talking to myself, staring at the screen. But here it goes. We'll see what happens. Another thing, I wasn't sure if I should do this in Bosnian or English, but I was advised in English. So these slides have been translated back and forth. So we'll see what the content looks like. All right, so just a little bit of an intro about myself. I was born in Gatsko, long time ago, seems like in 1983. Lived there during my early childhood. During the war, we moved to Mostar, where I spent another 9 years of my life. And then finally in 2001, we made a third migration to great United States of America. Is it a final migration? Oh, well, who knows? Sometimes I feel like I've either been cursed or blessed with these migrations and movements. But they most certainly, all of them individually educated me and taught me a lot of things. So I started from these little hills in Herzegovina. I ended up in these hills in Colorado. So it seems like we found each other eventually. Similar views, similar environments. But I'd say I've been blessed. It hasn't been an easy path, but definitely a challenging and an educational one. So next slide, I'll go over my education, my career very briefly, and then we'll get into talking about RF engineering. That's why you're all here. So I've started my schooling in Gatsko, obviously, but finished it in Mostar. And the reason why I wanted to list elementary, that's not what you typically see on CVs and resumes, but I firmly believe is extremely important. And that's where I learned my first well, obviously, we all learn the fundamentals of math and physics and chemistry and science in general. And the rest of it is really just an upgrade. And if you went to a good elementary school, you are destined to have a good education and good career path. So I'm a firm believer of that and huge supporter in education in general, but elementary especially. I finished high school in Mostar, Stara Gimnazia, from 97 to 2001. Again, very broad education, not very practical as we now see it in different schools. Not a lot of practical knowledge, but nonetheless a strong foundation for everything that came afterwards. Got my undergrad in electrical engineering at the University of Colorado in Boulder, and you can see a little logo down there. Really started the first 3 years I finished in Denver, and I worked and went to school at the same time. But at one point, especially for the last couple of years, when you start doing a lot of labs and research projects, you really have to dedicate yourself to school, and that was kind of the decision point. As you can see, a huge gap between undergrad and grad. Once I graduated, I started my family and my long dream of having children and family. We've been blessed with 2, 8-year-old and 10-year-old. And then after a while, it took me a while. So maybe some of you will be surprised, some of you may not. We grew up in a culture and tradition where if you finish the school in your 20s, you finish it. If not, then it's too late. But I've learned throughout my career that once you start working and you quote unquote finish school or graduate, it's really when you first start learning and applying all that great knowledge you've been accumulating over the years. And that's really where the real practical curiosity starts and you want to know more. So I waited for a logical point to go back to school, to grad school. And the logical point for me was when my kids were a little bit more independent and kind of got on their feet through in education world as well. And I started system engineering. The degree was a mechatronics degree, which is a mix of mechanical, electrical engineering. And now they changed the program a little bit, and so it's called system engineering. I'll talk through it a little bit, but system engineering is almost especially for Lockheed Martin Corporation. We'll talk about subsystems and different parts of satellites. And the integration and collaboration is of utmost importance, and it makes a huge difference, both schedule and design and budgets. So we'll go through that. Career-wise, I've started my engineering career as a research assistant and RF research assistant nonetheless at the University of Colorado at Boulder. I was working for Professor Edward Huster as well as Professor Zoya Popovic. I actually had 4 different professors from ex-Yugoslavia, if you will, and they've been extremely supportive and helped me throughout my education, which was quite a treat. My first job out of school was for a company called Agilent. For some of you who are not familiar, Agilent really used to be HP. You're the well-known computer producer and a provider. And at one point, HP has split into 2 different corporations, one to make computers, and the original one, really, HP started as a company for test equipment. And so that's what Agilent became, almost that original branch. And I worked there as a field engineer. My career in Agilent was great, but unfortunately it required the move to California, which at the time didn't really make sense for my family, and that's why I ended up working as a design engineer for EBSL Space Products Company, and later on they were bought by a bigger battery producer called EnerSys. So I worked in their space division. And that's really how I got introduced to space and all the advantages and disadvantages of working as an engineer for a space industry. And I'll kind of go through that later in the slides when we talk about challenges. After that, I moved to Lockheed Martin. That's really where my career started. I should have put some dates here, but that started back in 2011. I started as their production or manufacturing engineer I led a second shift team. I really did everything. This production was specifically for electronics. We have in Lockheed, we have number one, different companies or different divisions, and in each division has these smaller groups. So one of my reservations before moving to a big corporation was, oh no, I'm just going to be a little screw in a little part in this giant conglomerate, and I'll never be able to make my own mark. And to my surprise, I realized that Lockheed is built out of these little families, if you will, or little small companies. And so as a production engineer, I supported electronics production. And mainly, we don't do much of a circuit designs and circuit card assemblies. It's more of at the module and box level, but I'll go through that later. My career has been a battle between technical and leadership. So I've been kind of going back and forth throughout the years. But the logical step out of engineering was managing programs. And what that does, it kind of takes you away a little bit from the technical aspect, but it gives you a different perspective on how businesses are run, how teams are led, how where the money is in schedule and all, that entire game, how it all comes together. So it was a really useful way of me kind of making that switch, if you will. I ended up the next step. If for any of you who have worked in this environment, you'll know that production and quality don't really get along really well. Really well. Quality is we used to call it a necessary evil. The quality of product, especially for everything, especially for space industry, is of an extreme importance, because once we make our products and they go to space, we can't just go over there and fix them, right? So quality is extremely important. It's seen as a no value added because they don't do actual work or assembly, but they make sure that we stay within the requirements, and that our products, once they get built and tested, they will be able to survive the mission, right? And not just the length of the mission, but all the functional requirements, and they can perform and deliver the results that the customer pays for. So I was a little bit skeptical about my role in quality. As I said, we used to bump heads, but again, it gave me it was a gift and a curse, but it gave me a fantastic perspective on, again, our products and business. And my latest transition in the career has been to RF engineering. Again, most of my career with Lockheed has been in a production operations environment, and so engineering environment is a whole new, or you may think it's a little bit weird that I use this term, but it's a whole different culture, different way of doing business, different collaboration between people. So again, it's been a learning experience. All right, so get off this soapbox. Let's get into why we all dialed in today. So what is RF engineering, which is also called the microwave engineering? Not sure, again, this is kind of a one-way road, so I'm talking to myself, so I don't want to bore you with too much detail, but at the same time, I don't want to just briefly go over it in layman terms and really waste your time. But basically, as you may know, the higher the frequency, the lower the microwaves. So the lower the waves, because they have that inverse relationship, right? F equals 1 over lambda. And that's as far as I'm going to go into formulas. So don't run away. I hear a lot of people tell me, well, I've never heard about RF engineering, or what is radio frequency engineering, right? But I'm sure if you ever went to electrical engineering school or took a class, I'm sure all of you, or even physics, you all heard about Maxwell's equations. And that's what RF engineering is, right? It is once we get to the higher frequencies, really anywhere between 20 kilohertz to 300 kilohertz, gigahertz, sorry about that. Now we're outside of your typical normal circuit theory, and now we're talking in terms of electromagnetics, and we have to consider all the different aspects, or how the signals are influenced by both electric and magnetic fields, and that's what Maxwell equations are, right? Basically, these equations are mathematical models for either electric, optical, or radio technology, and really goes from anywhere from power generation to electric motors to wireless communication, radars, etc. So if you look at the bottom of the screen, and between 3 kilohertz to 300 gigahertz, you can see, and I'll go through this a little bit in my next slide, where these frequencies are used, where they fit in. So we look at anything between the maritime or submarine radio and navigation, through your amateur radio, TV, cell phones, and then the extremes, the high level frequencies we are now talking about, satellite communication, Wi-Fi, etc. So we'll go to the next slide. One of the things what makes the microwaves or high frequencies appealing or useful for the satellites, especially, or radars, is that the microwaves they have several different properties, and I just want to mention these real quick. They travel in straight lines at the speed of light, but what makes them interesting is that they're minimally refracted by Earth's atmosphere, and they can be focused in narrow beams, which means you can maximize the power and the communication transfer. All right, so let's go to the next slide. The little catchphrase we use for this conversation is why was RF engineering considered black magic? These days, not as much, but as we explore this technology in this industry, but like I mentioned earlier, at the microwaves or at the high frequencies, all the familiar circuit theory concepts that we have learned in school about all of these passive components no longer apply. Basically, under high frequencies, once we, electrical and magnetic fields kick in, now we have to consider their effects on the circuitry. And as you can see from this very simple diagram, even a simple wire, but in your circuit now becomes a series connection of the resistor and the inductor, right? So it's now in your circuit design, you have to consider all the different losses or the different gains, all the different effects of these additional components. So earlier in the history or technology development, once we got into the RF realm, the circuits as we knew them did not behave as we expected them, and hence the word black magic, because the whole RF engineering got this, I should say, a reputation that it's unpredictable. You don't know what it does. It's just a black box, and you put a signal, and who knows what you're going to get out, right? And so even to this day, when we go through different testing and troubleshooting, the tuning and the investigation process of the test failures are much more involved, and you have to open your mind to different possibilities than you would do in a normal circuit at a normal frequency, such as the power circuits or command circuits, etc. All right. So in terms of application, there are different ways of calling different range of frequencies. There's in IEEE, I have it in backup slides, but they call the frequency bands by different names. And if we have time, I'll show you how those, and it's typically one letter. So you have the X band, S band, K band, etc. Or this is one of the ways of classifying the frequency ranges. So it goes anywhere between extremely low to extremely high frequency. And as you can see from the slide, each frequency band has a different application. So we start with the extremely low frequency, which is typically used for maritime radio and navigation. The medium frequencies are used for amateur radio, as well as the weather forecast. I'm sure at some point of your life you have seen these codes on the TVs or different devices in your house, VHF, UHF, and this is really what they stand for. It's a very high frequency, ultra high frequency. So those ranges are used for your television, the FM radio in your house or in your car. And then finally, once we get into super high and extremely high frequencies, this is now we're talking about the latest technologies, which is cell phones, the Wi-Fi you have at your home, the astronomy, the satellites, etc. So my branch is space. My current branch in the work that I do is space. So I will be giving you kind of a brief overview what space communication is and what I deal with, and then give you a couple of examples of some satellites that I personally worked on that Lockheed has built. Again, not meant as a sales pitch for Lockheed or anything. Is really the intent of this webcast, at least in my mind, just to open a little door for you and kind of educate you on the resources. All this information is accessible online, so if it sparks your interest, and I'll be here as your resource if you want to learn more. All right, next slide. So I'll be mentioning some of these orbits in my in my subsequent slides. So I just want to kind of give you an idea what these orbits are. So really, typically you hear about LEO, MEO, and GEO orbits. The HEO or HEO orbit, it's really specific to polar regions. The LEO or the low Earth orbit, it's at the altitude between 100 and 1,240 miles. Typical uses for this orbit would be for the imaging, surveillance, science, and communication. So one of the example would be Hubble Space Telescope. So Hubble Space Telescope would be at this orbit. The medium Earth orbit, or MEO, it's between approximately 1,200 and 22,000 miles. This is ideal for navigation, giving kind of an optimum position for Earth coverage. So that's why GPS satellites are using this orbit for navigation, timing, and location information. And again, I'll show some slides on that, so you will see how that looks like. The GEO is at approximately 22,000 miles. Really, these geosatellites, they match the speed of Earth's rotation. So basically, they rotate at the same speed as the Earth, which from our perspective, they look stationary, right? That's why they're called geostationary Earth orbit. So again, it's used for communication, for weather, missile warning, and so this is the orbit where GO satellite is located, which is the weather forecasting satellite. And we have a couple of slides in a video that I'm going to play in my next slides. And ground stations. That's where we are on the planet Earth, and where we receive all these different signals from these orbits. All right, so very quickly about satellites. So this is RF engineering application in space. So satellites are divided in two major categories of the satellites, or two major configuration components. It's buses and payloads. So bus is really the body of the spacecraft, and which contains the payload and all the subsystems. So that is, if you will, a core of the satellite. The payload, I would call that a brain of the satellite. That's where all the instruments are carried for the primal, for the main mission purpose. So the optical payloads, for instance, that's where they would be, optical instrumentation. Then we have antenna deck that is used to receive and transmit signal to Earth back and forth, as well as to other satellites. There's a propulsion. So big propulsion is a subsystem, and big portion of that subsystem is really all the thrusters that allow the satellites to get where it needs to be, but they're later used for position adjustments, right? So we have weather in space that affects the position of the satellites. Depending on the sun exposure, there's always going to be a minor adjustments, and that's what the propulsion system is used for. And then finally, solar panels. That's how we get our power. Not necessarily, there are other sources for power for the satellites, but the main one are the solar panels. All right, so RF engineering space, RF communication. So specifically, again, if I look at all these different subsystems, we're looking at the electrical power, we're looking at the command and telemetry handling, right? And RF communication is just part of it, right? So some of the components of the telecommunications subsystem, or TT&C, tracking and telemetry and control, are some of the components that I listed on here. Major components would be the antennas. We have RF switches, we have diplexers and filters, and these are just a subset of the whole set, but I just kind of wanted to underline those. Antennas are used to receive, but also transmit signals. The most commonly one that we use is the reflector antenna. It's in a parabolic shape. That's kind of typically what we use, but there are other ones as well. Communication can go three ways. It can go communication with the Earth, which is what we call, if it's from Earth to satellite, that's called the uplink. If it's from the satellite to Earth, that's called the downlink. But the third one, that's kind of more explored these days, more researched, is called the crosslink, and that is the communication between the satellites. Lately, we've seen a lot of satellites that are built in these little constellations, if you will, like GPS satellites, and they'll communicate with each other. The RF switches, they're one of the bigger components of the TT&C subsystem, and they're used to route the signals through transmission paths. So the RF switches are used for both the uplinks and downlinks, right? So it directs the traffic, if you will. The diplexers, they're also passive devices, and they allow both transmitting and receiving. So they're enablers. So if we consider switches like a police directing the traffic, diplexers allow them to do that. And then finally, as kind of a component that I decided to list here are the filters, and they're super important because they minimize signal distortion. As you can imagine, in space or in general, signal transfer can be affected by many different things, right? It can be affected by radiation, can be affected by weather. There is this very specific category that filters that we have to use to deal with the rain, right? So rain distortion. So they're all kind of different. Then, signals get in each other's paths. And we have to help them again direct that traffic. So filters will help us do that. And I chose this one quote from our Vice President Tom Malco as kind of intro to the next slide, and it just kind of shows how encompassing the RF communication is in general, and we don't always see it that way. The world depends on RF communication to drive commerce, connect people, and strengthen global security. So I'll give a little bit more details in the next slide. I hope you're doing okay with the timing because I'm just talking to myself. All right. RF engineering. So here's one example of our satellites. It's the GPS satellite. And believe it or not, this little cartoon is a depiction how GPS satellite looks like. GPS stands for Global Positioning System. So typically when, and this is how I used to think, and typically this is what the stereotype is. When we say GPS, we immediately think communication, we immediately think cell phones, right? And so kind of taking that Tom Malco quote, I just wanted to give you a little bit of a menu, if you will, what GPS is used for. So GPS goes anywhere from recreation, right? So the weather positioning, obviously when you do the hiking up in the mountains for your positioning, right? For the altitude, for all those readings come from the GPS. Aviation, obviously, so seamless navigation and making sure we have a safe and efficient communication for the aviation traffic. I mentioned the maritime earlier. Again, more efficient traffic routing and the port facilities, right? We talk about public safety, so accurate mapping in a disaster region, for instance, extremely important. Road and rails, military, obviously, so using precise location navigation and timing for coordination of allied forces and weapon guidance. So historically, before the troops on the ground can communicate with their base, it would take days, right? And it would take, back in the day, people would have to, actually physically go from one place to another to let them know what's going on. Now we have established that communication literally within seconds. Power grids, agriculture, finance, and banking. So anytime you swipe that credit card when you're buying something in the store, that is GPS doing, right? So just kind of to give you an idea that the broad spectrum, if you will, of the GPS satellite. So the second example that I have on here is the GOES, which stands for Geostationary Operational Environmental Satellite. This satellite has a very long history. It started back in 1975. It's contracted through the National Weather Agency, but Lockheed has built the last two that have been launched, and there are two more coming, which are actually in the process of being built and tested. Altogether, there are 17 GOES satellites between 1975 and today. Mission is anywhere between 10 to 15 years. GOES R series satellite is the first satellite that Lockheed has built, and I personally had the pleasure of supporting the electrical power system electronics or boxes and the command and data handling boxes. So it was extremely awesome opportunity to learn about all the great things that this satellite does. So GOES was launched back in March in 2018. So like I mentioned before, these satellites, they orbit above Earth's equator, same speed as the Earth's rotation. So from our perspective, they're not moving. They're this, you can mistake it for a star in the sky. So if you look it up up in the sky and there's light standing there, that could be a GOES satellite. It's located at 35,000 kilometers. And basically, these weather satellites collect information and they transmit, right? We talked about the RF communication to Earth and back and forth every 30 seconds, which is amazing. I'm sure I don't have the data with me, but with the first GOES satellites, I remember a presentation, it would take days to get the first image, right? And now almost instantaneously. And one of the reasons why I put this website here, I just wanted to make you aware, there's another website on next slide. But basically, all these images we're getting from GOES satellites, they're public knowledge. They're available at the NOAA website as well as GOES website. So anybody, any one of you can go up there and see what kind of information we're receiving. So I wanted to show you a quick video again, public knowledge. It's on YouTube. Two videos, really. One is a cartoon and the other one is a little bit more serious. But it kind of tells you about the mission, what GOES does, and then I'll give you a couple of mind pointers. So, and if I mess something up in transmission, let me know, but I should still be sharing my screen. But this was kind of cute. It's a cartoon video, and I'll let you watch it real quick, and then we'll go back to our presentation.
Okay. I'm Gozar.
Oops. Pause it.
I'm a new high-tech satellite that will be orbiting 22,000 miles above Earth. I can see a lot of cool stuff from up here, and I take pictures of it with my spiffy camera that has 16 different settings. I have such good eyesight, I can see clouds, snow, smoke, smog, and ash, so I can warn you about dangerous conditions and help you avoid them. When storms are brewing, I watch them closely and help with hurricane, tornado, and flood warnings to help keep you safe. And my new lightning mapper will track lightning strikes way up in the sky, even through dark, dense clouds. I also help with search and rescue missions. I listen for distress signals from emergency beacons and tell search and rescue teams just where to find people who need help. But even when I'm keeping a close eye on Earth, I'm monitoring weather out here in space, too. I watch the sun for big bursts of energy, which send waves of radiation toward Earth that can affect power grids, block communication with planes, cause errors in GPS, and damage satellites. Space weather is also very dangerous for astronauts working outside the International Space Station. I warn them so they can get inside where they'll be safe. So the next time you watch a weather report or check your phone for the forecast, remember, that's me. So look to the sky and wave. I'll be here.
You gotta admit that was cute. But in all this cuteness, there's tons of useful information. So the latest, let's see if I can turn that off first. All right, let's go back to our presentation. So I'm not gonna show you the next video because I don't know how we're doing with time, but there was tons of great information in that video, meaning that the latest series, so the next generation series, GOES-R and GOES-S, have a lot of added capabilities, the new camera systems. They can be used for lightning mapping, and lightning mapping is important because research shows that if there is not individual lightning, but there's like a big group of lightning, that may be one of the predictions of the tornadoes. And tornadoes, from the weather perspective, are hardest to predict. And even a few-minute warning makes a huge difference. It can cost a lot of people their lives, not to mention the damage to their properties and whatnot. Another interesting fact that I learned from working GOES and understanding its capabilities, the newest satellites, because of these enhanced imaging capabilities, can track smoke and dust. And my question, I remember one of the VPs was giving a presentation, like, why would I care about the dust? And so I'm sure you're all smart cookies and you've heard this before, but I personally didn't. So he said, well, each drop of water, so drop of rain, needs a speck of dust to form a drop of water or a drop of rain, right? And it's easier. Obviously, the water can form in a drop by itself, but it's much harder. And they said if they observe the images of the sand movement in Africa, right? And so depending on the sand movement across the ocean can actually affect, or they can help them predict the hurricanes at the East Coast, which to me was kind of mind blowing. So it was awesome, interesting fact again that you can learn about. So I've added a couple of different links. This video is also super useful, not cartoon, goes a little bit into more detail on the application of the GOES satellite. This is the NOAA website where you can find tons of information, pictures, data, if you're interested, just kind of out of curiosity, what kind of info we get from satellite. And then I also included the Lockheed website where you can find some more information about the RF centers and what they do and what they do and kind of different opportunities or even jobs. So as a kind of a wrap up, I think we're doing okay with time. What is the future of space exploration in general, RF communication specifically, and just what are the challenges of the RF engineering, right? So generally speaking, the future of space exploration, and I mentioned here robotics and the telescopes for the physical exploration. And the reason I say this, we are very limited, very constrained in space because of a human factor, right? All of our astronauts, when they go up there, they come back with, they're exposed to radiation, they're exposed to no gravity, right? So their bones are affected, their blood is affected by all these different factors. So how deep in space we go, we're very limited, right, as a being, right? And then not just us, but also our technology. One of our biggest challenges in the space industry is the rocket. How far the rocket can go with the power that it has, right, with the fuel. So one of the things that's super limiting and kind of the most important factor we have to take into account in space industry, RF communication as well, is weight. So we're always looking for technological solutions that are light, that they're not as heavy, right? And that really drives the fuel consumption. And then how long it can sustain, or how long it can survive the radiation. Now we're talking I don't know if you heard about Orion mission. That's the first manned mission that we want to get to the Mars eventually, but we're using the International Space Station as kind of a stopping point to refuel our vehicles and continue deeper into space. So again, robotics, artificial intelligence, as you hear now, that's kind of a buzzword in tech world, is really why we're looking in investing into that, because humans are limited how much they can survive in deep space. Because of that, and another aspect is the cost. So it takes a lot of money to build a satellite and go to space, and a lot of these space companies, including Lockheed, are very risk adverse, which means they a lot of times they use very old technologies because they've been flown before, they've been qualified for space, and it's not as easy for them to risk using new technologies. So that's why NASA, and I mentioned this as an example, right? And many companies do this. NASA awarded $4 million to, I believe, 12 different companies to research, how do we partner in space? How do we use each other to help down this path? Encourage them or give them money to look into optical communication, how to change CONOPS, how to transfer secure signals so they're not stolen or affected by these different factors I mentioned before, etc. So it's really to encourage out-of-the-box thinking and try to get them to take more risks with these new technologies. So that's kind of, I'd say, a bucket of different things. But again, as the RF engineering, our challenges are building equipment even at higher frequencies than 300 gigahertz, right? The higher frequency ranges we go, the further we can go, the cleaner signals we can transmit. But the technology, all the parts we need for our boxes, for our systems, are not always available at those frequencies. So it's a constant investment, constant research right? To develop these technologies so we can put them together and put them to good use. So I think that's it. And I really want to leave some room, some time for questions. I believe that was my last slide. It is. So Anna, if you want to take over, if you're still there. Hopefully I didn't talk to myself.
But we surprisingly do not have questions yet, so I'm gonna give them some time
Okay.
to think about this, and maybe you can go back to that second video, since we do
Okay.
have enough time.
Yeah, we can do that.
Right.
I'll take feedback too if you don't have questions, like talk slower, you know, or something. So let me do this. And so if you think of questions after the fact about career growth, let me pause there for a second, or jobs or industry in general, don't be shy, and I will give you my email, so I'll be more than happy to answer that. All right, here's the video.
Changing. And the better we can predict what's coming, the better we can prepare. The GOES-R series, known as Next Generation Geostationary Weather Satellites, will be a game changer for weather forecasting. For the first time, GOES-R, which will be called GOES-16 once it's operational in space, will be able to monitor the Earth in near real time. Using a powerful new instrument called the Advanced Baseline Imager, GOES-R gathers data and imagery about weather over the Western Hemisphere as frequently as every 30 seconds. This enables NOAA to gather data with 3 times more channels, 4 times better resolution, 5 times faster than before. Faster, more accurate data means better observations of phenomena like severe storms, fire, smoke, aerosols, and volcanic ash. But this is not the only new instrument aboard the satellite. GOES-R is flying another powerful technology called the Geostationary Lightning Mapper. This instrument not only measures when lightning strikes the ground, but also lightning activity in the clouds that is charging the atmosphere. Researchers have found that an increase in lightning activity may be a sign that tornadoes will form. GLM will change the way forecasters look at severe weather to provide faster and more accurate warnings. All of this new technology means forecasters at NOAA's National Weather Service will have valuable tools to improve predictions of severe weather events, like hurricanes, providing faster warnings to emergency managers to help save lives and protect communities. Space weather is serious business in the 21st century, as much of modern life relies on sophisticated electronic systems. Working with other NOAA satellites, GOES-R will observe space weather with a suite of instruments that collect information about radiation hazards from the sun. Space weather can interfere with communications and navigation systems, damage satellite electrical systems, cause risks to astronauts, and threaten power utilities. NOAA launched its first geostationary satellite more than 40 years ago. Since then, the invaluable data from GOES satellites has been essential to countless industries like aviation, sea transport, and communications that rely on weather data. Sitting 22,300 miles above the Earth, the advanced technologies flying on the GOES-R series of satellites take weather forecasting to new heights.
All right, there you go. That was the second video.
And that was just about enough time for us to get 2 questions. And one feedback. The feedback is I would like to thank the speaker for an amazing webinar. And I would definitely agree that this was like a documentary, I swear. And
Appreciate that.
And the first question is how the general public is protected from overexposure of RF electromagnetic energy.
Hold on, I don't know if that's me. Let me turn off the... Yep, that was me.
We start off with the ABI.
All right, sorry. Can you repeat the question real quick?
Of course. How the general public is protected from overexposure of RF electromagnetic energy.
Right. So one of so part of the requirements, right, or when we even as early as the sorry about that, it's my door. Even as early as the design, we have a very strict ranges that we can operate in terms of just in general for the users, right? For people that are building these technologies, but then later on for the people that are exposed to them. So it's highly controlled by the health agencies that work with the space industry as well.
And the second question is kind of related to this one, so you can kind of incorporate it. What amount of RF exposure is generally considered safe?
I'll have to get back to you on the actual levels. I can tell you that anything we experience from what we are, in touch with daily, like microwaves, phones, television, computers, right? The power levels really is what you should be concerned about, right? That's really where the concern comes from, are super low. So can you hold just for a second?
Of course.
Hold on. Let me see if I can mute myself here. Okay, sorry about that. Right. So the power levels, I please take the name or just general public. I'll get you the exact levels. I can look into it, but I can tell you it's nowhere close where it will be harmful for us. So even at the International Space Station where we send our astronauts, even the levels that they see within the station are not even close where it would significantly harm them. The biggest problem with the astronauts is deterioration of their health over years. So if they spend the more and more time they spend in space, they'll see the harm on their overall health, mainly their bones. But again, please take a name, and I'll make sure I get you the exact numbers.
Make sure I forward the contact. And we have another question.
Sure.
How accurate predictions are right now, and how can they be improved?
Predictions in terms of what? Predictions in terms of weather?
Yeah, I assume that's what she meant. It's not specified, but like I assume that's it.
Right. And so I'm wondering the same thing, because it seems like even here the forecast they say it's going to be sunny, and then here comes the snow. So there are different aspects of the forecast, but I can tell you, considering we receive information on the approach of these storms and the movements of the clouds, again, is within literally 30 seconds. That's pretty darn accurate. And so, but the technology hasn't stopped. We're moving to do this even faster. The biggest challenge, like I mentioned, are the tornadoes. Even hurricanes, you can watch the cloud formation and their movement, but tornadoes have always been the toughest ones to predict, just the way they form, and you never know if they're going to form or not. So from that aspect is not as accurate as we want it to be. So right now, I believe we're down to, I think I'll have to check, but like around 10 minutes warning, which doesn't leave a lot of time for people to search for the safe place to hide. But again, that's what the purpose of this technology is. And look at like I mentioned, they're looking at the lightnings as kind of a symptom for tornado, right? So they're looking at the different things. So I'd say the accuracy is pretty darn close. And considering that we receive information so fast, but it can definitely be better, and the research hasn't stopped.
Okay, and I actually have a question of my own.
Yes.
Is there a way for countries that do not have this type of technology to sort of like pay for the service? So say Bosnia wants more accurate predictions, can we hire an American company to kind of?
Yes. Yeah, so the recent trend is, and I would encourage our country to go this way. You have almost, I don't know if you heard, like people will buy a vacation spot and they'll share it. So the same thing with satellites. So different countries, you can have up to 10 countries, or I'm making the number up, but like recently Japan and Korea just last week launched a JCSat satellite where they paid it in half, right? So you can, there's a main core of the satellite and there is payload. So different countries can invest and pay the payload to have their own dedicated. But to your point, they can also pay for the service. So even currently with our TV stations, they actually pay a fee to be able to pick up the signal, right? That's why you pay for the TV and for your cell phones, right? It all comes from GPS satellites. They're not Bosnian owned, but that's how the service is charged for. But I would encourage, and I really hope we get to the day where believe it or not, Rwanda got their payload recently, in Korea and all these different countries. So I really hope we go towards that, so we don't have to pay those high fees and we can own our little space in space, if you will. Another feature that I want to mention to you real quick, each satellite, regardless who it belongs to, has a search and rescue capability, and the video kind of mentioned that in the GOES. So if there's ever an emergency, or if there's somebody gets lost in the sea or wherever, the search and rescue is available for that, regardless whether it's your satellite or not.
Thank you so much for the responses and generally the presentation. I think this is the webinar I've learned the most in regards to things I already didn't know before. Like
that's awesome.
This was completely foreign to me, and I think to many others, and it was really detailed enough to give a clear picture. So it seems we have no more questions. So
yeah, that was kind of the challenge, to keep it balanced, not to overwhelm anybody. But I'll write a quick note. Really, the purpose wasn't to like completely shock you, but to kind of open a door. And if anybody has ever any questions, let me know, and I'll be more than happy to share the resources, because a lot of this information is available for general public. You just have to know how to search for it.
You definitely achieved that. I'm really stoked. Thank you so much. And like the people that asked the questions also thanked you for such a detailed answer. And it was really an amazing webinar. Thank you so much.
Awesome. Well, it was a pleasure, and thank you so much for giving me the opportunity. I appreciate it.
Well, have a nice evening.
You too. Bye.
Bye-bye.